and share the screen. All right, can you guys see my screen there? And if you have questions, please put them in the chat or speak up. And what else do I need? All right. So in the previous class, we were talking about what is the difference when things are traveling fast and how basically the relationship between mass and inertia. So can somebody give me the definition between the difference between mass and inertia based on the definitions we talked about last class? Arthur, you remember?
What?
What is the difference between inertia and mass?
Inertia is like how hard it is for force to affect something, correct?
Right. And how much, basically how much energy you needed to move it, right?
Yeah.
So the question was, if two observers are moving, no, if there's two observers, one is moving very high speed and the other one is not, with respect to some object, do they agree on the inertia of the object? And you guys all said that they didn't see the same inertia. Because the one that is moving fast, in his frame of reference, the other things are moving fast and so forth. So now this is the object moving really fast. All right, so according to my notes, I asked you a couple of other things. Basically, I wanted to get to the E is equal to mc squared formula, but we didn't get all the way to that. However, what I wanted to do today is related to that. And the first thing I wanted to do was tell you about, give you this, I'm trying to draw on something different because Zoom makes my handwriting be too wiggly. So if we look at different quantities, I'm gonna put a table here with some quantities. And then the first thing is this an invariant quantity? The second thing I'm gonna ask you is if there's a conservation for it. Okay, so let's start with the first one that I have on my list, energy. So I'm putting in a poll and asking you yes or no. All right, can you see the poll? Hold on, that's the wrong question. There we go. You guys can see the poll at this point?
Can you rephrase the question again?
All right, so the first question is, can you see the poll, yes or no? And you guys are clicking on yes, okay, perfect. So now let me give you the real question. So I'm gonna ask you for some quantity, whether you think it's invariant first, and then a second question, whether it's a conserved quantity. And in the first quantity we're considering is energy, okay? So is energy a invariant quantity? Is energy an invariant quantity? All right, we need 2 more people to vote. So the 6 of you said yes, it's invariant. And the answer to that is no. Why is it not invariant? Let's see, Christian? Why is it not invariant?
I guess because it can't be like changed. I don't know.
So if you're traveling really fast and I'm not, right, with respect to some object, whatever it is, are you gonna see the same energy that I see on that object? So it's kind of like the similar question to what we were talking about last class that Arthur just answered, right? If I'm moving with respect to an object, in my frame of reference, that object looks like it's moving. And if it's moving really fast, does it have more inertia or not in my frame of reference?
It shouldn't have more inertia. It should have less inertia in your frame of reference.
No, it should have more, right? Inertia
Should
is
it?
only going to go up.
Oh.
So we're in the same frame of reference, me and the object, and I measure and I look at it and I look at its mass and I look at its inertia, they look the same. But if I go to a frame of reference where the object is moving really fast in my frame of reference, it could be that the object is at rest, but I'm the one moving, right? If it's moving really fast with respect to me, then it has a lot of inertia, right? And that means that inertia and energy are related to each other. All right, so then another question, another quantity. And this next quantity would be the internal energy. And the question is internal energy invariant? The first one was total energy. Now this next one is just the internal energy of the object. Remember, total energy has kinetic energy inside of it. Internal energy does not take into account the kinetic energy of the object. All right, and I need 2 more people to answer. And the majority this time said yes. Exactly. And the answer is yes. So in this case, the internal energy is not related to the motion of the object, right? So the internal energy is more associated with the mass. So it's associated with the mass of the system. So you don't change mass just because you're traveling fast or not, but your inertia does change. You don't change internal energy if you're in a moving reference frame with respect with somebody else. Your internal energy remains the same. All right, so now we have invariant that's related to your frame of reference, frame of observation, right? But now we have something else, which is whether energy is conserved. Conservation of energy, right, is not the same as energy being invariant. So the new question is energy a conserved quantity? Is energy a conserved quantity? All right, so is energy a conserved quantity? That's the question up on the poll. All right, and the answers were more on the yes than on the no, and that's correct. Energy is conserved. And then you can guess what's the last question, right? Is internal energy a conserved quantity? If something happens, do you have an event? Do you keep the same internal energy? All right, so this one is not super clear. I'm waiting for one more person. Yeah, I think it's clear who's gonna win. All right, perfect. So we got 5-2 here. And the answer is no. So as an example, you have that the total energy is a sum of your kinetic energy and your internal energy. So with that, and you guys see my pointer right now, right? It's circling around the internal energy. All right, perfect. So if you have internal energy, is whatever energy is not related to your motion. So kinetic energy has to do with your motion. Therefore, total energy is also having to do with your motion because some of it is kinetic energy. So now if you're looking at the kinetic energy of a system, is that gonna depend on whether it's moving with respect to you or not? If you're moving at the same speed in the same frame of reference as the object, then its kinetic energy is 0. So therefore the energy is not invariant. However, this internal energy doesn't have to do with the motion. So the very famous equation that you're familiar with is energy is equal to mc squared, right? Everybody has seen this equation at some point already. So what does that equation mean? What that equation means is that if you have an object, and I don't remember if I went over this, so maybe this is where I was trying to get to and I didn't finish talking about it. So you guys can let me know if I have already covered this. So let's say that I had two objects. So this is at time 1. And this is at time 2. So my system is that I have a proton over here. And the proton is moving in some direction, moving fast. And then here I have a system that is a proton and a neutron. And you guys are familiar with protons and neutrons, right? Does anybody have, everybody has seen them? You can just point up or down with your thumb in the chat. All right. Anybody don't know what a neutron is? Just speak up. All right, so if you have a system that is a proton and a neutron, so a proton by itself is just a positive quantity. If you have a system that is a proton and a neutron, together, they're bound to each other, and they form a nuclei that is very similar to a hydrogen nuclei, but now it has an extra mass. So it has double the mass because a proton and a neutron have almost exactly the same mass. Not exactly, they're off by a little bit, but it's kind of like adding 1 to 0.9999. So now the mass of the deuteron is very similar to having two protons together, but not exactly, but its charge is just 1. So it's because it has an extra particle around it, is called a neutron. And for instance, if you take a proton and have the electron next to it, you have a hydrogen atom. If you grab a hydrogen atom, and actually 2 hydrogen atoms, and you put them next to an oxygen, you form water, right? So some of you may have heard of deuterons in terms of making heavier water and things like that. So deuteron is a particle that exists, is very abundant. And now what happens is that, let's say that you have the proton coming by, is passing nearby, and it's going to collide with this deuteron, right? So in the second picture, what I'm going to have is that now we're going to have here a proton, another proton, and protons are identical to each other. And then this neutral particle, the neutron, all joined together like this. So if we have a system, nuclei that has, so this is the deuteron, and this is the proton. And these two guys together, the proton and the deuteron, actually make a helium ion, and it's helium-3, because its mass is, its atomic number is 2, but its atomic mass is 3 because it has 3 particles that weigh about the same. So having those 2 particles collide also releases some radiation out. So those 2 together make radiation. And the thing that we have then to consider is, with this E equals mc squared, is what happened, where is this radiation coming from? And what happens then is that the mass of the proton and the mass of the deuteron let's say that this was a mass of 1, this is a mass of 1, and this is a mass of 0.9999. If we added them all together, we would think that we would have a mass of 2.9999. But it turns out that if we look at the helium nuclei and weigh it, it doesn't weigh 2.9999. It actually weighs less than that. And the mass of this guy, the mass of the helium 3 ion proton nuclei, sorry, I get my words confused, plus the energy of this guy, this is some radiation, right? Electromagnetic radiation. Those two add up together to that 2.99999. So you can actually see this radiation coming out and detect it. And you can also measure the helium nuclei and measure it, and they add up together to the original mass of the deuteron and the proton. And that is where we get that mass is conserved. And sorry, that energy is conserved. And some of that energy is conserved into mass. And some of that energy is just irradiated as electromagnetic radiation. Is that clear? Any questions? All right, so then let me move to, did that get moved over there? Okay, got it. So what I wanted to cover today then is give you an overview of a huge field of physics. Is a lot of people get into physics because they're really interested in this particular field, which is called high energy physics. In high energy physics, what you have is that people build these facilities. So this, let me change the color of my, okay. This right here, it's a huge building. There's a huge parking lot in front of it. There's a huge parking lot on the side. And there's a huge lake, well, not really lake, but like a man-made thing here. And you can see that this gets dwarfed by this huge ring that is here. And then there's another huge ring down here. This is a particle accelerator outside of Chicago. It's called Fermilab. And what they do is that they have protons that get accelerated to relativistic speeds. And because they're moving super fast, they have a lot of energy. A lot of it is kinetic energy. Their internal energy is still the same because they're still protons, right? But when you have all of this motion of the protons coming together and colliding, they collide the two protons like this, what happens is that they have so much energy that sometimes they create, that extra energy gets released as particles. Does that make sense? Please ask questions if you have any. So this is a particle accelerator. That's the largest one in the US, is called the Fermilab. And they have been colliding protons with each other for the last 40 years or so. And then what they do then is detect what comes out after the collision and what kind of particles are formed there. So this right here is not exactly the same thing. It's another, so this is a round accelerator that moves the protons in a round circle. But this one right here is actually how you would accelerate the electrons in this system. So this is another type of particle accelerator. And what you have is that you have a source of, in this case, electrons right here. And then you put little cans, metallic cans, and these metallic cans, C1, C2, C3, and C4, they're metallic in the tube. They're just little metal containers. And then you send a signal to them and you charge them either positively or negatively. So you have that an electron sees the negative or positive charge and it gets attracted or repelled, but then it's starting to move. And then the one in front of it is now attracting it because of the electric field that is created there, right? And the one before it is repelling it because it goes from positive, negative, positive, negative, positive, negative. So the potential across in this area is positive, negative, positive, negative, positive, negative, and this one is the opposite. So when the electron is attracted by this guy, it gets attracted, it gets to here. It keeps moving because he was already moving, but then this one changes sign and then it starts pushing on it and this one starts attracting them. So there's an electric field constantly accelerating it, whether it's pushing it in that direction or pulling them in that direction. And at the end, depending on how many cans you have here, you will get that the electrons can be accelerated at really high potential. You can also accelerate protons the same way, protons or electrons, because they're electrical particles. So this is called a Van der Graaf accelerator. So it looks, this is opened up. It actually looks like a beer can. In fact, when I was an undergrad student, I got to work as a REU student at a facility in the University of North Texas where they had one of these particular ones. The particle accelerator is called the Van de Graaff accelerator. And I don't know if you're familiar with Van de Graaff accelerators. Have you guys, does that ring a bell? Is something with a looping, kind of like rubber band, and then on the top they put a sphere, a metallic sphere, and then you go and touch it and your hair goes up. Are you guys familiar with that? So that's the same principle at work here. So I don't know if you have seen that demo or tried it yourself, where you just get charge into the metallic ball, and if you touch it, you get a shock. No? All right, so this is the design here where the voltage gets changed across these little parts right here. And therefore the electrons or protons, whatever you're pulling out of them, get accelerated and come out at almost relativistic speeds. If it's large enough, you can get it to accelerate to whatever energy you want it. And then the beam travels, in this case, these are different lines of the beam, each connected to one of these guys. And those electrons or protons are traveling through here. So you want them to travel through a system that is at low pressure, very a small number of particles there. So it's not like in normal atmosphere, but you actually put it into a vacuum and reduce the number of particles that are there, because if you have your proton passing by, it is going to crash into whatever molecules you have there. Yeah, go ahead. If you have a question, go ahead. All right, and then I think this is from the old, in the chat, I see that is that a photon? Yeah, so that was a photon back in the picture of the radiation coming out. All right, so you have that the protons are passing by. This has to be a straight line. And you put a target somewhere and then you crash protons into them. So that's the experiments that I was a part of. And actually when I got there, we had to fix the machine that looked like this. Oh, and I didn't finish telling you, the one in one of the ones in UNT is actually paint like a Budweiser can. So they took the cover off here, but the cover is just looking like a can around it. And yeah, they painted it like that. So finally, when you put these things, you have to make sure that the beam is perfectly aligned. So we spent about 6 weeks making sure that the beam was aligned. So there's like all of these jacks right here. This is kind of like a giant jack. And there's different things that you have to align. So for instance, this is, the beam comes here. It's passing through here, the beam of protons. Well, this thing right here, what it is actually the pump to get the air out of the system. So when you put the pump here, you just have to connect it and make sure that this is still straight, because just tiny little deviations of it are going to screw up the beam. You have then that if you're putting this here, and then you put the next one, what you do is kind of like a copper gasket, and then you tighten it really hard and compress the gasket so that there's no air leaving the system. And when you're tightening it up, you could move things a little bit. And therefore you have this box right here. This box is so that you can move it in this direction or that direction if it got moved, and then you have the jack to move it up or down. And then the final thing is that you don't want anybody to just bump into it, because that took your whole week of work. And you have to start over again and make sure that it's straight from all the way over here, just because somebody passed by and bumped it over here. So it's very sensitive until you put all the jacks and solidify it together. So particle accelerators are really important. In fact, there's a proton beam therapy for cancer. And what they do is that they accelerate protons. Maybe not exactly this type of machine, but some of them do have this type of machine where they have the Van der Graaf type of accelerator, accelerate protons and get the right speed. And it could be relativistic speeds that you're getting there. All right, so with that, let me try to get, all right. The question for you guys, if we have a nuclear reaction, so similar to the picture that I put over here, where is it? This one, right? So this is a nuclear reaction where you have the proton hitting the deuteron, giving you a helium. So this is the conversion of mass into energy. And the question for you guys to answer as your homework is as follows. So that nuclear reaction that I showed you before is, the first question is, how much mass is lost? So, basically all you have to do, right, is figure out how much the mass decrease. So if you have a mass of a proton, and you can look this up on the Wikipedia. So the mass of the proton is about 1.6726 to 19 times 10 to the 27 kilograms, okay? Then you guys will be doing the deuteron. Figure out what is the mass of the deuteron. In kilograms too, if you're using kilograms. If you're not using kilograms, it might be a little bit harder. I mean, you can do it too without knowing the mass in kilograms. or you can use kilograms. And then what is the mass of the helium particle, helium ion? So this one is the first part. So figure out what is the change in mass. And then the second question would be, what is the energy of the electromagnetic radiation, which it is a photons, coming out of the reaction? All right, any questions? So if not, I wanna let you go early because last time I kept you over. And if you have questions about how to do it, just let me know, okay? That's it for today. And this would be uploaded this is going to be uploaded to YouTube, and I'll add it to the Canvas website so you can see the question if you need to. And it'll be due next Wednesday before class. Thank you.